Okay, this is the tutorial for the memory allocation problem set, and we're looking at question 1, or the top of it anyway. So just to familiarize you with this bit of code, let's look at the main. It does really two main things. It creates a mutex and it creates a thread, and then it starts the kernel. So if I look at the code for the thread up here, it acquires the mutex, it prints hello, and it releases the mutex. So it's a very trivial application. The whole point of it was to show how you can statically allocate the control blocks and stacks that are used by the real-time operating system and avoid using the heap altogether, which in safety critical real-time systems is important. And so if we look up at the top, the first thing that's done is we're defining the stack size, because we're going to allocate it statically here. Whoops. So we allocate the space for the stack right here, and the amount of space we're allocating is 2048 bytes. And it's just an array, and it needs to be double word aligned or 8-byte aligned, so that's why I use the uint64 type, because that's an 8-byte data size, so it will be 8-byte aligned. And then I just divide, you don't want stack size elements, you want stack size divided by 8, so you get that many bytes. And that is used in the thread attribute down here, where we tell it the address of the stack, and also we tell it how big that stack is. Now let's see what else. So we've got a control block that's used for the thread, so I'm working backwards here, and so the size of that is defined in a header file that's included, rtx.c or rtx_os.c if I remember right, and that is, I tell you down below, is 28 bytes. So anyway, so we point the control block memory in this thread attribute to it there, and we tell it how big it is here, and so the OS will use that storage for the thread instead of dynamically allocating it. And then we do a similar thing for the mutex. And sorry, just to back up, so for the thread attribute, that's used here when we create the new thread. So we pass it a pointer to the thread attributes, and that's where it gets the addresses from and the sizes when it creates the thread. And going back to the mutex control block up here, again, the size here is defined in that header file, and it is used in the mutex attribute structure here, and we set this field to point to our data, and we tell it how big it is, and then that is used, we pass a pointer to that when we create the mutex. So all the storage up here, which are globals and are allocated statically, are going to be created at compile time, and they're going to be used instead of dynamically allocated storage by the OS. We do have another global variable to be aware of, and that is the mutex here. So let's go down to the first question then. So the first question is, calculate the amount of data segment memory used by the application, and it gives you the size of the mutex identifier types and the two control block sizes. To figure out how much data segment memory is used, we want to look at what are our global variables, and we've got 3 of them, 4 of them, 1, 2, 3, and 4. And we could look for static variables, but there aren't any in this code. So we just add up those 4 sizes, gives you your total, and so that's a fairly straightforward question once you know what to look for. Question 2 says, what is stored on the call stack for the main thread and the worker thread? And so local variables and also the the invocation records. So if we look at main here, let me just switch my color because it's all marked up. In the main, we have a local variable here, a local variable here, so the mutex attribute and the thread attribute structures. That's it as far as local variables, and it calls a number of functions. So it calls OS kernel initialize, it calls OS mutex new, it calls OS thread new, and OS kernel start. So we're going to use the stack to allocate storage when we when we call those functions as well. And likewise for the worker thread, there's no local variables, but it does make 2 function calls here. So if you go back and look at the answer for the main thread, we've got our 2 local variables, and then we've got the activation records. That is storing the function linkage so that it can enter that function and then return later, so it saves the context of the function. If it's any of its data might get modified by the functions it's calling, and so on. The worker thread has no variables, and so it's just the activation records for, oh, I missed printf. So if I scroll back here, we've got OS mutex acquire printf and OS mutex release. Sorry about that. Okay, and probably the most complicated question is part 3 here. And so it says, suppose that RTOS2 automatic allocation is used instead of static allocation. And it will depend on the implementation what automatic allocation is, but we're going to assume that it's going to be using the heap. And so it says that assume that control blocks and the worker thread call stack are allocated on the heap. I'll underline that in green there. It also says assume that printf doesn't use the data segment or heap. It probably doesn't use the heap. It probably does have some static variables, because printf, at least in the past, has not been reentrant, which means it must have some kind of global state. And it says calculate the amount of data segment memory and heap memory used, assuming the heap is implemented as described in the notes. And there's a hint here that the free list, which is used by malloc and free, is a global variable. So that's going to be in the data segment. And then it gives you a couple other assumptions. Assume that each entry in the free list has 2 4-byte pointers, so 8 bytes per entry. And also it says remember that there's 1 hidden entry at the start of the list. And I'm going to go talk about that now. So let's just go look at what I showed you in the notes. So this is the free list from page 2 of the memory allocation notes, and you know, each implementation by each compiler will be somewhat different, but this is roughly what glibc does, the GNU standard library implementation. And so over here on the left you see it says that there's 64 bins, and if you count that up there's actually only 63 there. So those are the exact size bins. I did add a note at time 3 minutes and 7 seconds that says there's actually a 63 plus a hidden bin. I'll expand on that in a minute. And then there are 63 sorted bins here. Now let me just go over to the source code. So this is the latest copy of malloc from the GNU standard library implementation. If you look at line 1586 here, it says that the number of bins is 128, but then if you look above that it says that bin 0 does not exist. Bin 1 is the unordered list, which I haven't talked about, but it's like a cache for very recently freed blocks. It's just an implementation detail. So if you look a little bit up there, lines 1568 to lines 1574 are roughly what I showed you in the lecture. So it depends how you count, but let's just say that there's 127 total bins, and go with that. Okay, so let's say that there are 127 bins in the free list. They're 8 bytes each, so that gives you 1016 bytes. There's still the mutex there, it's still 4 bytes, and that's everything that's in the data segment. So let me just go back to the code quickly. So I will mark up what would change. So if you were doing this using the automatic storage instead of statically allocated storage, you get rid of that data up there. And the other thing that would change is you wouldn't need this. You would replace this with null. You wouldn't need the thread attribute structure, and you would replace the pointer to it with null. And then you're using the automatic storage allocation. So all you're left with is one global variable here, the mutex, and that's that. So we just have our free list, we've got a mutex, and there's our total size of 1028 bytes. It says to assume that the thread stack is allocated from the heap, which seems pretty weird. There's different ways that it can be done, but if you're just creating new threads as the program runs, where else would it get the stack storage from? So anyway, the assumption is that it's allocated on the heap. We need to figure out how much heap memory is used, and so we are going to have the worker thread stack here, and so that's going to be 2048 bytes. Now the thing is that there's 8 bytes of overhead for each chunk. So let's just look at this 8-byte overhead by looking at page 3 of the memory allocation notes. So here it is here, and I showed you the chunks that were used, and I showed you there's the allocated chunk versus the free chunk. And they are always allocated with some extra storage. So let's look at the free chunk. So at the top of it you got the size, and then at the end of it you also have the size, and then some forward and backward pointers. Or we can look at the allocated chunk, and it's got this extra size information at the start and then the data. Anyway, the way it's implemented, there's always at least 8 bytes of overhead on top of the size of what you asked to be malloced. Okay, so that's where that assumption comes from. And the size is rounded up to the next multiple of 8, and that is just the detail of the malloc implementation that things need to be double word aligned. So that's why that's done. So going back to the thread chunk size here, we've got the stack size plus the overhead, and then that's going to be rounded up to the next multiple of 8, which is the same thing as 2056 bytes. And then we have the two control blocks, the mutex control block and the thread control block, and we're not creating them in the we're not creating them explicitly in the application, but the real-time OS still has to allocate space for them dynamically on the heap. And we already know the sizes of those. For the mutex, it was 28 bytes. We had the 8 bytes overhead, that's 36 bytes. You round it up to the nearest multiple of 8, and that gives you 40. Similarly, for the thread control block is 68. It's the actual size plus 8 bytes overhead. That's 76 bytes rounded up to the nearest multiple of 8. And you've got 80, so you add up those three values and you get 2,176 bytes, and that's the whole problem set.